Okay, I'm solving on camera problem 1853. And what do we have? We have a pair of rods, same length, same mass. AB rod is hinged at the ground at point A, and at B, the other end is hinged was the second rod, and NC of the second rod is running horizontally through a horizontal line through A by the use of this roller, which is massless. And then we have a spring with an initial length of 1.5 meters, rate 20 newtons per meter, and it's applied, the ends are between at A and C. And when theta is 60 degrees, the system is at rest, and it's allowed to displace, and due to gravity, the weight of the two rods, they are further stretching the spring, and we want to know what the kinetic energy, or rather the angular velocity of rod BC is when theta is 30 degrees. Okay, so I have here some annotations. Actually started the problem, so let's see what we have so far. So I drew the system in an arbitrary position, theta, and I summarized what's given. So mass of AB equals mass of BC, 12 kilogram. I call it mass, M. Length AB equals BC, call it L. L0 is the free spring length, K is the spring rate. And then if you look here, when position 1, when theta is 60 degrees, this triangle ABC is an equilateral triangle. So distance AC is 2 meters, longer than 1.5 meters. So at initial position, spring is already stretched. And then when theta is 30 degrees, there is further stretch of the spring. Distance AC, it's 2 square root of 3 meters. How do we get it? You just take twice 2 meters times cosine of 30 degrees. Cosine of 30 degrees is square root of 3 over 2. So times 2, it's just square root of 3. And 2 is the length of the rod. Okay. We're going to use the elevation relative to the horizontal AC of the center of mass of rod A and of rod AB and rod BC. Again, because of symmetry, the same height occur irrespective of theta, or okay, and that's equal to half. It's in the middle. L over 2 that is, and then sine of angle theta. Okay, so that's the elevation of the center mass. We're going to use, of course, energy conservation. We have a gravitational elastic potential. Kinetic energy originally is 0, so initial kinetic energy plus initial potential, total potential energy, equals kinetic energy when theta is 30 degrees going from 60 degrees, and then gravitational potential and elastic potential, that is total potential energy V2. So again, this is 0. So let's see what V1 is. We have two masses, so it will be 2 times mass of one rod, m times, or the weight of one rod, m times g, and then yg, L over 2 we said, times sine of 60, plus elastic potential, that's 1 over 2k times the stretch of the spring square. So stretch of the spring in initial position is 2 minus 1.5, that is 0.5 squared. And I calculated the potential energy, total potential energy, as being 206.397 joule. In the second position, when theta 30 degrees, I have 2 times weight of a rod, L over 2 sine of 30 degrees, same as above, and then same as above, that is with the new angle, And then elastic potential, the new stretch of the spring, 2 square root of 3 minus initial length of the spring squared, and the value is smaller because of the rods dropping their center of mass. It's 156.297 joule. Final, or position 2, kinetic energy is going to be kinetic energy of the two rods combined. We have one rod that's rotating at A and the other one that performs a general planar motion. So we can, let's see, so rotation of about fixed axis, we can use this second equation, rotation about, using mass moment of inertia about the axis of rotation. So 1 over 2 mass moment of inertia about the pin joint omega squared, and that's going to be omega of rod AB. Okay, so I have kinetic energy of bar AB as it's rotating about A, so 1 over 2 I of one rod about its end, omega AB squared, plus 1 over 2 here for the second rod, it performs general plane motion. We can use either equation 18.6, velocity squared times m divided by 2 of the center of mass plus 1 over 2 moment of inertia about the centroid omega squared, or we can use the centroid formula. So 1 over 2 mass moment of inertia about the centroid omega squared. Now, being distinct bodies, these omegas would be different. We're going to see that they're actually squared, at least they are the same. Why is that? Because if you look at this angle theta, it's also this other angle here, and we have theta dot is going to be omega of AB. This other angle dot, that was going to be omega of BC. And actually they both rotate, so really omega of AB and omega of BC, it's the same. We're going to see this in just a little bit. But for right now, we're assuming them to be distinct. What are the moments of inertia for bar AB? If you go to the back of the book, so moment of inertia, a slender rod about its end is 1 over 3 ml squared. That's what I have here. And then for, like I said, I'm going to use the instant center version of the energy, kinetic energy and general plane motion. So 1 over 2 moment of inertia about the centroid omega squared. Okay, so what do we have? We have, I said that mass moment of inertia of about A, about that end point, is 1 over 3 ml squared. And then I need to find the distance to the centroid from the instant center. And how do I get the instant center? First, I know the velocity of point C. It's perpendicular to AB at B, and the velocity of point C, is going to be perpendicular to the line that connects point C to the instant center. Okay. We can also say velocity of B is omega of AB times distance L, which is distance AB. And then we can also say velocity of B. This is in order to calculate omega of BC. So velocity of B is omega of BC times the distance from B to the instant center. All right. So again, instant center, you get it by extending these two lines, A, B, extended, normal on the horse over the vertical at C, extended, And so this is 90 degrees, 90 degrees. So we're going to see if this angle is 30 degrees. This is 30 degrees. This is going to be 60 degrees. And likewise, this angle is going to be 60 degrees because I have 30, 30, 60 minus 180, 120. So 120 plus 60, 180. Okay, 60 degrees, 60 degrees. This cannot be but 60 degrees. And if a triangle has all three angles equal to 60 degrees, is an equilateral triangle that is all sides equal. It means that this is 2, this is 2, this is 2. All right. So it means that B to IC equals L. It means from these two equations, because VB is the same, means that omega AB equals omega of BC, and let's call it just omega. All right. This is just because of the particular configuration was equal length AB and BC. And of course, for the position theta equals 30 degrees, that's a simplifying situation. All right, so I stopped when I was in the process of writing mass moment of inertia about the instant center of rods BC. So centroidal moment of inertia from the back of the book is 1/12 ml squared. So centroidal moment of inertia of a slender rod plus is going to be mass, parallel axis theorem, mass of the rod m times the distance from the centroid to the instant center squared. The distance from the instant center to the centroid, G BC, and so this is GBC, okay. It's going to be from this right angle triangle with a 60-degree angle, it's going to be what? 2 sine of 60 degrees, which is 2 times square root of 3 over 2 square root of 3 meters. Okay, this is the distance from the centroid to point C. Okay, or you can get it from Pythagoras theorem. So you say 2 times 2, that's 4, minus 1 equals square root of, do I have it right? So 2 squared, that's 4, minus 1 equals, so square root of 3. Hold on. So I have 2 times 60 sine equals, and then what have I missed? We said that alright, so this is square root of 3 over 2. Yeah, was a mistake. So it's just square root of 3. Luckily, I verified. Sorry for this. Meters. So we have the distance from to the center, and of course this is going to be squared. So it's going to just the squared value is going to be 3. Okay. So let me double check. Maybe it was a mistake here as well. So I had 2 cosine, so 30 degrees cosine times 2 equals, and then squared, let me pause. Okay, I'm back. I double check. I thought I have a mistake here with the distance AC not being 2 square root of 3 for theta 30 degrees, but it's correct. So everything's fine. I also calculated the moments of inertia about A about rod. AB, 1 over 3 ml squared, 16 kilogram meter square. And then for the rod BC, about the centroid, it's 40 kilogram meter squared. Okay, so we have now the kinetic energy T2 is going to be 1 over 2 times 60 times omega squared. Again, we agreed that omega is the same for the two rods, and use omega notation instead of omega AB and omega BC. And then plus 1 over 2, 40 times omega squared. Okay, so this is going to be equal to T2. So back to the original energy conservation equation. We're saying V1, that is 206.397, equals I can factor here omega, so it'll be 16 over 2, that's 8, plus 20 equals, so it's 28 omega squared. So I write it here as 28 omega squared plus V2, which was 156.297. Okay, so from the 2 we get omega equals square roots or power 1 over 2, so it's 206.397 minus 156.297 over 28, that's power 1 over 2. Okay, so I have 1 over 28 times parenthesis 206.397 negative 156.297 close parenthesis equals, and I take the square root. So omega is 1.3376 radians per second, and this is the answer. Okay, so this was the instant center approach. The other approach would have been to use to determine the velocity of the center of mass in order to apply equation 18.6. We can use instant center to find the velocity of the center of mass. I can find it right away. So velocity of the center of mass, velocity of G of link BC is going to be omega of BC. And by now we have it, you know, if we use instant center, by now we know that omega of BC equals omega of AB. But in any case, if we're to find omega of the center of mass, is going to be omega times distance from the instant center to the center of mass of BC. Okay, so, and we've got that calculated. It's square root of 3, so square root of 3 omega. Okay, and of course we can we can find the third approach is by not involving the instant center in any way, we using relative velocity. So we can say velocity of B, it's known, and I can say so velocity of the center mass of BC is velocity of B plus omega and these are vectors, plus omega of BC crossed with distance from B to the center mass of BC vector. This is from kinematics, and we have velocity of B as omega of AB times distance AB, and we'll have to write velocity of C equals velocity of B plus omega of BC crossed with distance BC now. And we know that velocity of C in the y direction equals 0. I take the vector off. So what multiplies velocity of C, the j component, is 0. So from these two vector equations, you get omega. Well, this also goes with the, so in addition I have two equations. We need to use the third equation being velocity of B vector is velocity of A, which is 0, times omega of AB crossed with distance with vector AB vector. Okay, so let's count 1, 2, 3 vector equations with the information that velocity of C in the y direction is 0 allows us to calculate or ultimately learn that omega of AB and BC is the same first, and then find velocity of the center mass center mass of rod BC. So I guess this is a more involved approach. We can use instant center just to find the velocity of the center mass, or we can use instant center with the kinetic energy about the instant center for the rod BC, which perform general motion. And this is the way I have the problem solved. All right, so this is it. Thank you for watching.